What I'm going to look at in this video is I'm going to look at the intersection of two lines in three-dimensional space. Now if we think back to 2D straight lines when we covered them back at National 5 and higher level, if we were to look at a point of intersection between the two lines, what we would do is we'd rearrange them such that we had both of them in the format y equals, or even just one of them is y equals, and then if they were both y equals we could equate them to each other and solve for x. Or if we had just one of them as y equals, we could substitute that into the second equation, solve them for x, and then substitute back in to get the y. And the key check for us at that point was to make sure we got them right. If we substitute the x and the y into either of the two equations, we'd get the same solution for both. Now that was a line in 2D. In three-dimensional space, we have to look at this in a little bit more depth, purely because we're at the third dimension. However, our steps are the exact same, just expanded to include another dimension in total. Now, when we're in 3D space, lines can have a set relationship to one another. Now, there's three ways that lines can relate to one another in three-dimensional space. They can either be parallel, they can either intersect at a point, or they can be skew. Now, what that means is they're not parallel to each other, but they never ever intersect. Now if we were to look, let's say imagine this is us doing a view into a room, and if I was to label this line here, so this edge of the room is AB, a straight line AB, and this one is a straight line CD, and imagine that they were both straight lines in three-dimensional space, I'd know that these two were parallel to each other. Now because they're parallel, I know they would never intersect or touch. If I was to do a similar one and look at AB and BD, what I'd notice is that these two lines, they're not parallel to each other and they both intersect at this point B. So those two straight lines in that three-dimensional space would do that. However, if I then look as well at the line AB and the line EF and compare those, what I would notice is they're not parallel to one another. That's quite obvious, but with the positioning of EF and the direction it's going, and the positioning of AB in the direction it's going, they'll never touch each other, so they'll be skew. So they're not parallel, but they'll never intersect one another. Now we have to determine this relationship and figure out how to get the point where they intersect one another. Now, to find the point of intersection, we just have to follow four straightforward steps. The first one is that we have to express both equations in a parametric form using the variables t1, t2, or parametric variables lambda 1, lambda 2, depending upon what text you look at, you may see one or the other. The point is you have to make sure that you don't make the t's equal to each other or the lambdas equal to each other, because what you can then do is equate the corresponding equations for x, y and z to one another, and that'll give you three equations, each with a t1 and a t2 variable in them. What we can then do as our third step is use any two of those equations as a pair of simultaneous equations to find the values for t1 and t2. Now that's two out of the three equations used. This third equation is then used as our checking equation. What we can do is substitute the values for t1 and t2 into this third equation. If they satisfy it, what we've found is they found a point of intersection. If it doesn't satisfy it, there is no point of intersection. So if that's the case, we know that the lines fall into one of the other two categories, i.e. they're parallel or they're skew. Now I'm going to show you an example of exactly what I mean and the steps to do it. So let's imagine I've got two lines. I've got one line with the equation x minus 5 equals negative y plus 2 equals z. And I've got a second one, x minus 12 over 5 equals y plus 3 over negative 2 equals z minus 5 over 4. I want to show the intersect and find that point of intersection. So let's call this one L1 and this one L2 to represent our lines. If I look at L1, if I was to write these in my symmetric form, which it is there, it would be the equivalent of me writing x minus 5 over 1 equals y plus 2 over negative 1 equals z over 1. Now what I'm then able to do with each of these is take it and put it into the parametric form for the x, the y and the z in terms of this, because what I'm going to do is I'm going to equate this whole thing to my t1 variable. So if I was to do that and look at the x, what I'd end up getting is that x equals 5 plus t1. I would get my y variable, so I'd be able to write that y equals negative 2 minus t1, and z is just equal to t1 itself. I could then look at line 2, so let's say the L2. So I know I've got the x minus 12 over 5 equals y plus 3 over negative 2 equals z minus 5 over 4. And I'm going to say that that then is equal to the t2 variable. So I'm going to set this equal to another parametric variable, t2. And what I'm going to do is the exact same, get this in parametric form. So I'm going to get that my x is equal to 12 plus 5t2. My y is equal to negative 3 minus 2t2. And my z is equal to 5 plus 4t2. Now what I can do is equate corresponding terms. So I'm going to equate the x's to each other, the y's to each other, and the z's to each other. If I do that, what I can then do is rearrange each of these equations so I can get a set of equations in terms of t1 and t2. So for the x's, I'd have 5 plus t1 equals 12 plus 5t2. I could rearrange it and get t1 minus 5t2 equals 7. If I looked at the y's, I'd have negative 2 minus t1 equals negative 3 minus 2t2. Rearrange it, and what I'd end up getting for that one is t1 minus 2t2 equals 1. And then do the same for the third one for my z. So I've got t1 is equal to 5 plus 4t2. So my t1 minus 4t2 is equal to 5. So now I can pick any pair of them and solve it for t1 and t2. So let's just pick the top two here. Solve them as a pair of simultaneous equations. So what I'm going to do is subtract the second equation from the first, because if I do that, I eliminate the t1 variables. So I'll end up with t1 take away t1, which is nothing. I'll then end up with negative 5t2 minus 2t2. So minus minus becomes a plus, so I've got minus 5t2 plus 2t2. So I get minus 3t2. That equals 7 minus 1. That equals 6. So minus 3t2 equals 6. t2 is equal to negative 2. And I can substitute this value for t2 into any of these two equations that I've used in order to be able to find what t1 is. So let's imagine we take the second equation there. I've got t1 take away 2 times negative 2 equals 1. So I've got t1 plus 4 is equal to 1. So t1 is equal to negative 3. So there you go. I've now solved it and found my values for t1 and t2. Now we do our check. Now that we've got this, we do our check by substituting into this third equation here. So if I was to do that, I'd have negative 3 minus 4 times negative 2, which is negative 3 plus 8, which is negative 5. So it works in my third equation. I've found the values for t1 and t2 that give me the required solution. Now I've got to find the point of intersection. So I could use either value of t1 and t2 and substitute them into either set as long as I remember it's the correct set. So if I was to use t1, for example, what I'd get is x is 5 plus t1, so I'd get 5 plus negative 3, so 5 minus 3, that would give me 2. I'd get negative 2 minus t1, so negative 2 minus 3, so negative 2 plus 3, which is 1, and z would just be negative 3. If I was to use this one here, my t2, what I'd get is 12 plus 5t2, now t2 is negative 2, so I'd have 12 minus 10, which is 2. I then have negative 3 minus 2 times minus 2 t2, sorry. So I'd have minus 3 times plus 4, which would give me 1. And then my z would be 5 plus 4 of the t2s, so it'd then be 5 minus 8, which would be minus 3. So it works for either value there, but the point being, we've got the point of intersection of those two lines in 3D space as being 2, 1, negative 3. Now when it comes to that final step, it doesn't matter which of your parametric values you choose, just remember to stick it in the right equation. Don't stick your t1 in here or your t2 in this one here, because you'll not get the right answer if you do that. Make sure you put them in the right equation at that point so that you can get the right point of intersection out. And remember the steps. Parametric form, there's your first step. Equate the x, the y's and the z's, there's your second step. Pick any two equations. Now try and go for the easiest two that will make it the least amount of work in. Doesn't matter which two you pick, so I could have picked the first and the third, second and the third, whichever ones I wanted. Bottom line is, you get your values for T1 and T2 from that, and then you use the third one, the one that you haven't solved, as a check. When you've done that check, you find which of your scenarios it is. So they either intersect and it holds, or they don't intersect and it doesn't hold. So if this hadn't worked out here, my values for T1 and T2 would not work for the third equation. So those two lines do not intersect because the parametric values do not give me the same coordinate. Ultimately, those lines wouldn't intersect. So we have to remember that. And then the final step, if they do intersect, we find the point of intersection by just plugging in the values of T1 or T2 into either set of parametric equations. Again, go for whichever one gives you the easiest set of calculations to do. It's not a difficult set of steps to follow. It is very, very similar to two dimensions. The only difference being is because we've got a third variable and we have to set up two parametric values, we have to use a pair of simultaneous equations to solve it. Two values, two equations needed. Bob's your uncle. Job's a good one.